I hope it won't crash again. Okay, good. So welcome to the 10th lecture on NLP with deep learning. And today we're going to be talking about one of the most prevalent models of these days. So everybody's kind of maybe using it in one or the other way. And this is the GPT family of models. And it's called decoder-only model, as we will see. So what we did before Christmas break is that we are talking about the BERT model, which is the encoder transformer architecture. So why is it transformer? It takes input and transforms into some other way of input in a way. So it just transforms the input text. And what is it doing? It's actually learning contextualized word embeddings or token embeddings. So we have an input, we tokenize it into some subword units, such as, using tools like VP encoding or other tokenizers. And then for each of these tokens, we are interested in its dense representation, which is a vector of some size in some low-dimensional space, because these tokens have dimensionality, or the vocabulary has dimensionality about like 50,000, for example. And we want to represent it as a dense vector in some space, and the position of this point in this vector space has some meaning, so similar things are closer together and things like that. So something we know from static word embeddings, but now contextualized, because as you know, static word embeddings has some disadvantages because of the multiple meaning of same words and context of words. So this was a short recap. So the BERT model can be used for, well, a couple of things. So we're talking about text classification. So we take a sequence of tokens. So text, for example, I don't know, what was it used for? Movie reviews, sentiment analysis, for example. So you take a text and want to classify it in a couple of classes. This is one sequence. Then we use the two concatenated sequences with a special separation token in between for example, NLI, natural language inference. And we also saw that actually for each of these tokens, since we're getting its embeddings, we can do something on the token level. And this was the sequence labeling task, such as NER and POS. So what is NER? What is NER? Yes. Name identity recognition. What is name identity recognition? Which is? Yes, exactly. Yeah. So you take each word and say like it's a beginning of entity, inside entity, or not an entity. Entities are persons and stuff like that. POS. What is POS? What is POS? POS. Power of speech tagging. What is power of speech tagging? Right, okay, so we're assigning a linguistic category to each token, which, actually a word, token word, which is verb, noun, and things like that. Exactly, okay, cool. So far so good. So we're again talking about NLP and transformers. Okay, cool. So here's again the architecture of transformer, where for each token here, in the input, we, after some input embeddings layers, do you remember what these input embeddings were? So we had input embeddings, and there were two sorts of them, the input embeddings for BERT. We have the standard token embedding, as we would have for other models like feed-forward networks, but there was something special about transformers we had to take into account. So some sort of special embeddings for transformer. There was the positional embedding. So we were saying for position 1, we have a special embedding. For position 2, we have special embedding until position 512, because this is the context size of BERT model. So we have embedding for each token, and we have embedding for each position, basically, independent of the token, and we sum them up. Okay, so these were the input embeddings, and then we had these transformer encoded layers, which was this complicated self-attention mechanisms with these scale products. We will be talking about it again today. And since we have, after each of these layers would take the input, well, it's actually a matrix. So it's a matrix where the rows are the tokens. So this is the input length. And this dimensionality is something we decide, like the size of the model, something like 768, if I'm not mistaken, for BERT. It could be some arbitrary number. And we are outputting mostly the same dimensionality of from each layer. And after a couple of these layers, where L is determined by what? Who says how many layers of transformers we have and why? So I can set it up. So how should I decide on that? Should I take 1 or 5 or 100? How much I fit in my memory, exactly. Because the more layers, the merrier, but then I need more RAM. So typically it will be something between, I don't know, BERT, 12 layers, something like that. Could be 24, could be 100, who knows. And then it was the final layer, which actually took these embeddings, so for each token, the embedding, and did a thing. So typically we could use it for, again, projecting the final layer into the vocabulary. So basically, for each word trying to map it to a vocabulary, this was used for this mask prediction. Mask language model prediction. And there was also this one special token, which was the first one, the CLS token, the CLS embedding, or there was a special CLS token added to the beginning of the sequence, and it ended up with the special embeddings. And in BERT, it was used for what? CLS token for classification. So we just use this as a representation of the whole input for doing some text classification. Any questions? It's been a while, I know. So I don't know, what did you do over Christmas? Maybe not be interested in BERT. Maybe yes, I don't know. But this is like a quick summary of what we were talking about. There was one interesting thing. I posted it yesterday. 2 days ago. I posted it into Discord. So we're talking about how BERT is still relevant in 2025, and because it's a model from, I guess, originally 2018, roughly 2018 was the first archive paper of BERT, and time has changed. Things has changed in 5 years or 6 years, like extremely. So is it still relevant? And there was a paper who actually took the BERT model, the architecture, the encoder architecture, and used couple of new techniques in the architecture, not changing that much, but just basically using a couple of tricks like different GALUs and different layer normalizations maybe, and just more tokens, more inputs, and just train like a modern BERT model. And it shows like great performance for the task we were talking about last time. This is the information retrieval. So basically a sentence representation, like sentence BERT. So for representing a sentence and then using this one vector for finding similar sentences, like in information retrieval. You would look for relevant documents to your query or to your document. And so, the jury is out. Who knows? You can take older model and just run it again on like trillion tokens. I think this was co-authored by NVIDIA, by the way. So you need to really know what you're doing if you're doing large-scale LLM, and you should know something about the hardware maybe as well. And it's pretty cool. So the same is, by the way, for LSTM, so long short-term memory. We're talking about LSTM in the middle of the lectures, and it's an architecture from, I don't know, like 1998-ish, something like that. So it's old and it doesn't scale, and that's why we have the transformers and things like that. Well, guess what? One of the co-authors of the original LSTM paper, Sepp Hochreiter, I guess is his name, and his group just published last year LSTM on steroids, like a new kind of reborn of LSTMs, which included a couple of tricks from transformers. I don't remember all the details of this paper, but they were showing, it's not that bad. I mean, this is old architecture, but if you just take it wisely and plug new techniques which we are aware of, then you might get some cool performance of the older models. So the jury is out. Pick up a paper, take something which is not in fashion today. I don't know, convolutional neural networks, and do some cool stuff. Scale it up to trillion tokens, and maybe you'll be in the leaderboard for 12 hours before somebody else comes with a new technique and then beat you again. Okay, good. So this was the BERT, and here's the thing. So the BERT is trained with this mask language modeling. So what does it mean? What was the mask language modeling? How did we pre-train BERT? How do people pre-train the BERT model? Remember? Yeah. Right, so we took the text and masked certain words. Which words did we mask? Or could we mask? Random, yeah, okay. Right. Exactly. So we would take I think they had 10% or 5% of the tokens and just basically replace the word with a special token called mask, which is like a blacking out the words. And the model has to learn or relearn, or try to reconstruct what the missing word was. This is one objective. There was another objective. Do you remember which one for BERT? It wasn't that important. I mean, it turned out not to be that important later. It's the whether two sequences of texts appeared after each other or were shuffled. So this is like the consecutive objective prediction. But mostly what actually really works turned out later in other following papers and research that actually the language modeling masking is actually what makes it learning some useful representations. So the thing is, we train this with masked language modeling. If you remember language modeling, what is a language model? What is a language model? So people ask me what's going to be in the exam. I'm always saying, and I'm saying again, like, well, I'm asking questions, and some questions I'm asking over and over. I'm asking over and over, what is a language model? What is a language model? Exactly. So language model tells you the probability of, or the probability distribution of a vocabulary, exactly, after seeing some context, which is like previous words. Okay, so this is a language model. It tells you, actually, it can tell you all, not only the conditional probability, what is the probability of a word after seeing this, but it can tell you the joint probability of a sentence, basically, because you can deduce one from the other. Yeah, this is a language model. So is our BERT a language model which tells you the probability of next word? Not really. Why? It tells you something about missing words, but yeah.
It tells you something about the meaning of words rather than.
No, if you train with the masked language modeling objective, it tells you what is the missing word. What is the probability distribution of a vocabulary of a position here of my missing word, given the context? So it's basically something like language model, but it's not really the language model as we understood before. Why? What is so special about BERT as compared to, I don't know, Ngram language models, which gives you probability of the next word?
It basically fills in like a, what we call like a gap text. So
Yeah.
you give it some gaps and it tells you like you have put 5 words here. So
Well, yeah, okay, good. I mean, you can, but if you, okay, that's a fair point. I mean, because you're masking multiple words at the same time. If you were masking just one word, let's say like we're just masking one word.
because BERT is based on context and not on the general idea of the language.
But language models also use context. You use context words to predict the next word. BERT is using the words to predict the word. So what's so special about it?
Looking at the entire input sequence.
Exactly. It's looking into the future. BERT can look into the future tokens. So there is, remember, we have the sequence and we're masking words. And we perform this self-attention over past and future tokens. Because we take a word and we mask random words somewhere in the middle. In standard language modeling, you have a sequence of words and are asking what is the next word. But you don't know what's coming after. You don't care about it. This is the main difference. That's why BERT is good in representing the whole sequence because it can look into the whole sequence. It just doesn't look into the left to right context. So it's not really a language model in a way as we understand, like take previous words and generate the next word, because it generates words somewhere in the middle. So can we use it as a true language model? Can we use BERT to generate text?
I mean, what if we always fit in like the previous sentence and mark the last word, and then we run it over?
Yeah, okay, so if we change BERT, if we change BERT and say like we're just masking the last word, then we can use it as a language model, right? But BERT as it is right now, is it for language modeling? Like generating text? Not really. Like, how can you generate text if you're just filling gaps in the middle of the text? Like, it doesn't take, what is the next word? What is the next word? But you're exactly on something. So we can turn it into language model when we just say, oh, you know what? Don't look into the future. Just take the past, do some attention or whatever, just take the previous, as in standard language modeling, like take the previous sequence of tokens and give me probability of the next word. Can we use transformer for that? Yeah, of course. I mean, with some hacks and some stuff, we can scale it up and to look similar as BERT. But we can use this for language modeling. So this is the key. That's what we're going to do today. So this is the idea of the decoder-only models. So, do we have to go into details of BERT again? Well, it never hurts. So, because we're going to be using this today later. Okay, so we're going to be using this this self-attention. So, I mean, basically what we are going to do is to take the BERT idea, the architecture, the layers and everything, and we're going to change it a little bit somehow that we only be able to look into the past, and we'll be generating just the last word. These are the two things we are going to change somehow in the architecture of the BERT to turn it into something else than not BERT, like basically the GPT model. So decoder-only transformer. So in order to do so, we need to understand again what is this self-attention, what is it doing. So again, this is the input of this self-attention. So what was this again? What is this matrix? Yeah. You.
The input matrix.
Say again?
The input.
Yeah, the input matrix. So what is, shape or something like that? Like how many rows and what does it mean? How many columns, what does it mean?
Columns are the side of the input. And,
okay, so each row corresponds to what? Each row corresponds to each token in the input. And the ordering of the rows corresponds to the ordering of the inputs. Okay, good. So, and the columns? Yeah, so like this is a projection into some space, which we decided on the dimension of the space. We don't know what they mean. So there are some columns, 700 something, and they have meaning, which is not clear to us as humans. Okay. So then there are the Q, K, and V. So we have the so-called query, key, and value linear projection. So what does it mean, linear projection? You take a vector. How do you do a vector? How do you project vector to another vector? You multiply by matrix, exactly. So you multiply each of these rows by matrix, which means at the end of the day, you're multiplying matrix by matrix. Well, what you're actually doing is, in any matrix by matrix multiplication, what you're actually doing is you're multiplying each row by matrix and just stack them up. And that's what we're doing. So we take each row, multiply by matrix, project to something else, and we do it for each row, so we get the same number of rows at the output. Good, so we have the query, key, and value. So, and this means these projections are learned. So they have, they are green, so, using the same color scheme in all the lectures, green means they're trainable. So there are some weights which we're going to train by backpropagation, gradient descent. So there are some weights. These are trainable. So we project them into Q, K, and V. Why should we take Q and K? Why do we need two, by the way? Because they're taking the same input and projecting to similar size of the output. So why should they be different? It's a good question. Why just don't we take Q? Because then we're multiplying them together here in the scaled product. Why not just one?
We can train different parameters.
Exactly. Because these parameters. Yeah, sorry. Go ahead.
Then we can have like a higher arithmetic degree in our solution and can think of more problem.
So first part, yes. The second one, maybe. First part, yes. Of course. So the query and key are, when they start training, they are initialized with different parameters. So they will learn different things at the end of the day. Also, there's a sort of historical reason why these are called query and key. And this comes back, we didn't talk about the original transformer paper. So there's a 2017, the most famous, most cited paper maybe, is the paper called Attention is All You Need, where they introduced the transformer architecture, which was consisted from encoder as BERT and the decoder as we are talking today about. And they were communicating together through this query and key. So basically, one part, the query was from the input, and the key, or the other way around, was from the decoder. And they were basically, two different kind of it's called cross-attention eventually. But in self-attention, we have these two things from the same input. Anyway, so then there's the scaled product. So after multiplying, we're making the dot product of these two matrices to get these row associations matrix. And then we're gonna softmaxing each row of those, which is basically giving the weight. So for which token should I attend to at which position, basically. And we're multiplying, so this is some sort of like weight matrix afterwards. And we're multiplying with the value matrix to get a final representation of these, of the head, not of the old input, but of the head. Then afterwards in the architecture, I think we're stacking the heads one after each other. The outputs of the heads we're stacking and then projecting by another linear layer to something which is the same shape, something like that. But the main idea of self-attention is query, key, and value in the dot product, which gives you the strength of association between tokens. So far, so good? This is like repeating from Bert. Yes?
And the dot product of two matrices was defined as like dot product of every row with each other, right?
So, I mean, no, scale. So we're not doing basically, if you take a vector, so, do you see, is it a vector?
Yeah.
Okay, this is a vector, and this is a vector. So from your side, okay, left to right. So this is a vector, and this is a vector. So I can multiply them and get what? Get one value. Okay, good. If they have the same length. They have pretty much the same length. Okay, so we have two vectors. If you have two vectors like that and do the dot product, you get what? No, dot product. What is dot product? You take two vectors like that, row vector, and dot product of those, you get what? One number. Which is the same as multiplying a row matrix by a column matrix is a dot product of two vectors. So, why is it called scaled dot product? If you take just one row, I mean, it's basically doing dot product for each row and each column for these matrices. If you have, okay, so this is a matrix and this is a matrix. If I do multiplications of these two matrices, what I get is another matrix. But basically, this is doing dot product for each column and a row. Okay, if you don't understand my hand waving here, just draw it. So dot product. Does it clarify your question? Cool. Okay, any other questions? Okay, good. So let's move on. So here's again the algorithmic depiction of this self-attention, but I'm gonna maybe go through it because it's just repeating from last time, and then I spent some talking about it already. So again, we have some input, we talk about it, what it means. We have some output, we also talk about what it means, and then the attention, single attention head in a way, is having projected Q, query key, and value. Then here's the formula for doing this first two matrices multiplied, which means basically all these dot products between rows and vectors, rows and columns. And here's just some scaling factor for better stability. And then we run the softmax over this. So this is what we were talking about last time in BERT, and now we have the same for a single query, which is basically just again the same thing, but more in detail for just if you have a single token, what it really means to compute attention for a single token. So if you don't have any questions, I would just skip that because we were talking about this last lecture. Okay, good. Again, okay, so here's an example for a single query unmask attention. So let's say we are at position 2. So token is position 2, and we have 3 contexts. So our context window is now just 3 tokens, or 3 tokens. And we did this projection onto key and query, and maybe the value later. So we have the query is this vector. This is just arbitrary. I just made it up. It's just numbers. This is the query vector, and we have the keys for first position, second position, and third position, right? Because we're computing the keys for each position from the input. So in the if we want to express it as matrices, we have the query vector here, and this is the transposed key matrix. For example, this corresponds to the first column, this is the second column, and this is the third column, right? And we just take them together and transpose because we're multiplying this, as we saw here, we're multiplying by the key transposed. And here we're taking just one query value. Okay, does it make sense? Okay, so this is just a workout example. So what we are now going to do is then we take, for each key, we take the dot product of this Q vector with each column. So what is the dot product of Q times K1? It's 11, yes? Okay, 35. What is the dot product for the second one? Okay, you do the math. I mean, it's 4, is it? 104. And what is the dot product? Okay, wow, interesting. Okay, what is the dot product for K3? So 11 times 7, wow, that hurts. 77 plus 8 times 12 is 80. I give up. So what is some number? 34 was correct, good. 104 was correct. And if you do the math, you have 173. That's why we have machines to compute dot products. So I don't want to do this at all. I can do this, but it hurts. Anyway, you should be able to know how to compute dot products, okay? So we ended up with these dot products. Okay, cool. So now these are basically the raw associations, right? So this is the raw scores. And then if we take this vector and run it through softmax, so what's gonna happen with softmax? What is softmax?
It gives the numbers, the values between 0 and...
It turns a vector into a probability distribution, discrete, finite. But there's this is interesting because, I mean, if you think about it, okay, I'm gonna turn 35, 104, 173 into probability distribution. So you can just kind of, in your head, you can just kind of squeeze it in between 0 and 1. What is really interesting is what the actual results looks like. Because it looks like that all the mass goes to the last item. Why is it so? Because this looks like, kind of linear, linear relation, but after softmaxing, it's like, wow, really almost 1 and zeros. Why? Why is softmaxing so brutal? So what is softmax? How will softmax look inside? So what is in there? What is nonlinear in softmax? You're right. I mean, it's nonlinear. What? Exactly. So there is exp of each of the inputs. Now do the math. I mean, if you do e to the, e to 104 and e to 173, which one is really bigger? Of course. So, and then after you're normalizing these things, basically the winner takes all. So this is it. It's kind of, for human minds, we can see linearities, but exponentiation is hard, kind of like to project, like tiny little difference, and it just blows up. Anyway, so after that, after softmax, we get these scores. And, okay, so any questions? This is just a simple walkthrough example. Okay, cool. So far so good. Good. So this is like from the previous slide, so we ended up with these normalization, with these weights. And what's interesting, so we are at position 2 for the query. And now we see that after the attention, position number 3 has the highest weight. So it means all the attention would be facing towards future, towards token number 3. Is it good? No. Yes.
Most of the context of need for doing something would be in the unknown world, right?
No. Okay. So what does it mean? Okay. So what are we doing with these numbers? That's the question we need to understand. What are we doing with these alphas? What are we doing with these alphas? Anyone remembers? So we take these alphas, and then let me come back to this algorithm. So we compute for each of the tokens, we compute the alpha. T, what is it? Yes. So this is alpha. So here we are just at one word, right? We have one word. And then we take what is VT? VT is the value. So this is the value which we projected before, somewhere, in the parallel here. So key query, and the value is coming here. And after the alphas, we are somewhere here. And now we're going to use these alphas to weight the values for each of the context. So which means this is just a number between 0 and 1. And this is like weighted average. So we're weighting all the context tokens from the value. And this one, which is the largest value of the alpha, gets the most attention, which means will be mostly represented in this final vector. So you can imagine if all these alphas are just zeros and there is only one which is 1, then it means like this token will be that important token at attention. So this is where the model will attend to. So paying attention to some other token in the input. So imagine like you have inputs, tokens, and each token might be interested in some other tokens because this is important for its tokens representation to know something about the context. So it's paying attention to other tokens, and it could be token from the past, could be token from the future, and it could be just one token, could be two tokens. This is it. This is the attention, how it works. So, and now it basically takes the token from the future. So is it a good thing? So does it answer your question? What is it? What does it mean now? Okay, everybody's clear on that? So we're position 2 and position 3 is in the future. So this is bad for any language modeling because of, as I said, let's not look into the future. So the self-attention as we have right now is kind of badly designed because it can look into the future. So what we really want is we want to attend only to previous tokens. This is what we want to do, right? I mean, language models, they can look into the past as long as you want. You can take the whole input, thousands of tokens, and that's okay. If you want to run self-attention or attention over the input, you can just look into the past, but never look into the future. So can we do this in a somehow clever way in this self-attention mechanism? So what we really want is that at position 1, well, so these are the position 1 corresponds to this row, position 2 corresponds to the second row, and so on, right? I mean, this is each row corresponds to one token. So at this position, we are not allowed to look into anything else. So this, no, bad. Never look in there. We can compute the self-attention, but never use these things. At position 2, here, so we can look into the past, that's okay, but these are no-go. No. Never look at them. Position 3, the same thing. We can look into the past, but never look here. And position 4, okay, so we can look in this. So what we really want is that after this softmaxing in self-attention, we want to give these things 0 probability by design. Like they cannot play any role because we cannot learn from them. If we give them 0 value, 0 probability, it means eventually, if there is some 0 values, there will be what? They won't play any role in learning, which means if you do backpropagation over 0, there is 0 input, there will be 0 backprop. So you won't learn from them, basically. So you basically ignore the future. So by assigning 0 probability, these will be ignored in learning. Nothing happens, no learning. Cool. So this is what we're gonna do, right? I mean, now we understand that we have to look into the past, but not into the future, and we can do it in this matrix form. Does it make sense? If we take the whole input as it is. So we wanna, for each token in the input, we want a representation and just only look into the past, but not into the future. But we're just not taking a single word, but just the complete kind of token sequence. Okay, so how can we do this? So I have a solution, which is bad, but it works. So, I mean, why is it bad? We'll see later. So, but so what we said, like we really want to do this. This will be 0, 0, 0, 0, 0. So then, I mean, okay, let's use for loop. So for each t so this is the length of the input. Input length, number of tokens. So for each input, for 1, 2, 3, 4, we do the key and the softmax scaling, and after the softmax scaling, we should just say for each tokens which is after the current index, give it a 0. So if we are here, for example, we do the softmax scaling and then assign 0. So it won't be like actually it won't be like true probability distribution afterwards. So maybe it's actually a bad idea at all. But generally like we want to be masking things out. So we just zero out the rest. So this could work. We assign zeros as we wanted. Will it work? Yes, I guess so. Is it fast? Why is yes? Yeah.
We cancel out very much of the mass. So, for example, in the mass thing, there is a lot of attention for something.
Yeah, that's a good thing. So exactly. I mean, this implementation is actually wrong for a reason. Because if you take a probability distribution, so this would be like position 1, 2, 3, 4, and this is a probability distribution. So this is what's coming after the softmaxing. Okay, so we turn it into probability distribution, and I'm saying I'm at position 2, and I'm just gonna zero out this. Then what happens if I just screwed up the probability distribution? It's not probability distribution anymore. That's correct. So I cancel the mass. The question is, does it matter? The answer is maybe not. Maybe yes. Because we don't care if it's like a true probability distribution. We just reweighting things. So maybe this would work. But actually, this is a bad implementation for other reason, which is the scalability. But what was your question again?
Smaller values, do they make learning less fast?
No. I don't think it's about like numerical stability, like the smaller or bigger values. It's just there is a bottleneck here, computational bottleneck. What is it? What is the computational bottleneck here in this algorithm?
Only just manually setting single values and not using like bulk vectors.
This is bad. Why is it bad? Why is for loops bad? Yeah, this is sequential, so you cannot parallelize things, you cannot run on GPUs, you cannot use the SIMD instructions and blah, 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 blah. So what you want to do instead is to vectorize things. You want to run it as much as things on vectors, because if this is vectors, you can just offload to GPU, and GPU will take everything in parallel, as much as possible. Or even like NumPy, or what is it called, SSE instructions, maybe vectorization on CPUs. But eventually, GPU's vectorization is important. So, avoiding for loops. No, for loops are bad. And actually, it was bad algorithm for the reason we kind of killed the mass, so it was wrong. But maybe it wouldn't matter. But what matters is scalability. So, we're gonna do something else. What we're gonna do is that before running this exponentiation, we just forget this. We're gonna put the mask here, so-called, so masking. We're gonna put a mask on the matrix by adding minus infinity to these values from the future. Why? Why is minus infinity a good value for preventing something to have any value? So what happens? Let me see. What is the softmax value at this position? Why?
Because the higher it gets, the higher the value, and it doesn't get much lower than -infinity.
So what is this? This is 0. That's the point. That's the point. E to minus infinity, if you know the exponential function, something like that, and very high, it's 1. And if it goes to infinity, it goes to 0. And if you implement it correctly, if you really can say like, oh, minus infinity, which you can in Torch, and if the function is implemented correctly, then for e to the minus infinity, you get 0, true 0. This is great, because it will keep, it will basically keep the probability mass now correct. It will be, a probability distribution after this masking before, but it will just basically, put value of 0 after softmaxing to all these future values. And you can run just softmax again in parallel, like for each row in parallel. Yes.
And you don't have to set these values to manually now because
Say again?
Why don't we have to set the values to -infinity by hand now again?
Yeah. Well, we can, but we don't have to do it like in for loops by iterating over each tokens. We just use the mask as masking in Torch, let's say, or NumPy. So there will be a very nice trick how to do this for the whole matrix with, how's it called? Mask? It's masking basically, right? Masking matrices in Torch or NumPy is the same thing. So you can put indices on things and you basically get a slicing or masking. So you can get a slice of the matrix and say like, oh, for these values, give me, put it, this value. And there's actually one function in Torch, if I'm not mistaken, that does it exactly for the upper triangle here, some sort of like filtering the upper triangle, and then you say like put everything -infinity, and the implementation will take care of that it's fast as it possibly can. So that's the trick. Because afterwards you have the mask, and then you run your stuff as usual. So, any questions with the masking? So the reason for masking is we're preventing from looking into the future. The reason are, never look into the future. It's a bad thing for language modeling because you never know what happened in the future. You can look into the past as much as you want. And the trick how we did it in self-attention is just by this masking. So it's called causal masking. Your causal means, there is a causality in time and you're preventing from leaking from the future. Yes?
Sorry, I still didn't really understand the difference. If we are going to use this mask trick, why can't we just still use the zeros as opposed to the negative infinity?
Here, the zeros, the zero trig here, you mean this?
Yeah. So instead of going over a for loop, why not just put zeros?
Yeah. So no, because I made this up, and this obviously incorrect because it doesn't. If you zero out things after a softmax, it's not a probability distribution anymore. That's the problem we're talking about.
Okay, so
And maybe it's better to keep it as really probability distribution because you want to sum things up. The weights should be distributed equally to all the tokens which contribute.
so the zeros with the negative infinity is more about masking than about the for loop.
Exactly. Yes and no. So how could you? So okay. Let's figure out the algorithm. How can you do this? So here, what's coming out of here? It's let me just clean this up. So what's coming out of here is a matrix. So after this one, you get this will be probability distribution. How do you get rid of those? How do you turn them into zeros? And as such as this will remain a true probability distribution for each of those. What could be the alternative? You can put them to zeros and then do some reweighting again. I think you can do this. Like put to 0 and then do just, maybe softmaxing again, or maybe just normalizing again, which is an extra operation. Here, you do like very quick mask here. So you say, oh yeah, you know what? These are just -infinities, and run the softmax as you can. So speed, like less efficiency, exactly. Okay, any questions? Good. So this is a left to right mask self-attention or causal attention, and here again is the same algorithm, but now here the for all is just how we write the algorithm. This is not how we implement it. Okay, so no for loops. There will be some masking in Torch how to do this efficiently, but what we're doing is saying if so the mask is, we kind of create the mask before. Is it possible? Yeah, we're setting the infinite. This is the important part. How exactly? So the devil is in the detail. It's like how exactly you implement this, and you have to do it vectorized form and as efficient as possible. So there will be no bottlenecks in computation in for loops. But basically, this is the only thing we changed here. Okay, so now coming back to the self-attention head in the transformer, again, we still have the, query key value, nothing has changed, scale.product, nothing has changed. Now we are adding the mask here. And then again, we have softmax and multiplying and things like that. So the only things we changed here, as opposed to the bird, where we can look into the future and the past, is just adding the mask. The rest of the architecture remains the same. That's it. This is GPT. The rest remains the same, more or less. So the left to right mask self-attention is, what does it mean? That the output from 1 to t depends only on 1 to t, so it can be used to predict the t plus 1. So we can really use all the information we had so far in order to predict the next token, because we know only the information from the past, and what does it mean? Okay, so let me try again. So here's the input. So tokens 1, 2, 3, 4, and it goes through the transformer. So the transformer, which means we have a embedding for each token. Right? I mean, this is what the transformer is doing. What we are doing with these embeddings is they represent the word as well as all the context. And in BERT, this token, or excuse me, like the last token, or let's say the second token. So in BERT, the second token have information from the entire input. So if we say, okay, here from these two inputs we want to generate the next word, like what is the probability of the next word, it would be cheating, because here we are actually looking to the future. So this embedding already knows what's coming after, so it makes no sense to predict. We can only predict, maybe we can take the whole input here and maybe predict what is the next token afterwards. That we can do. Okay, but with the self-masking, with the self-attention with causal masking, we can predict the next word from each token now, or each position. So here at position 1, after masking, we never saw anything from the future, right? Because we're basically like here, the only information that goes here is basically from the, excuse me, no. The only information it gets is just from the history, which is just the first token. So we can use this token to predict the next token. Okay, good. So if we're at position 2, we can use this input, the whole matrix, the whole context, and it never saw the future, so we can use it to predict the next token. Okay. At position 3, the same trick. Like at position 3, we have the whole representation of the previous input, and we can use it for predicting the next word, but we never saw this thing. And finally, of course, the last one, we can predict the next word. Okay? So this is why it's this causal masking is actually enabling us at each position to take whatever we have input and use it as a representation to predict the next word. Does it make sense? Okay. So why should we talk about this? Right. Okay. So this, what I just draw basically is pretty much what we are trying to reconstruct again. But let's give it a shot. So we have the input is sequence token IDs, and we have some trainable parameters. So all the weights, all the weights basically. And what is the output is a matrix of, let's say, probabilities, because these are numbers between 0 and 1. And it will be length of the input times size of the vocabulary. Okay, this is interesting. So exactly what we are. So if these were just embeddings, we can just project them again into the same thing. And this would be a probability distribution over over vocabulary, which means we would turn this into, this would be size of maybe 50,000, and this would be mostly values between 0 and 1. So 0, 0.0, 0.0, 0.99, and things like that, okay? So this is a distribution over probability distribution over the vocabulary, from which we're saying, okay, yeah, I mean, the next word here will be the one with the highest probability value, so we can sample from this distribution to generate the next word. If you remember, we did sampling from language models in the exercises. So we took the previous, we had this character-based language model. So we took like 2 previous characters and then predicted a probability over characters for the next one, and we say like, oh, we can sample from this distribution. So we use sampling with according to this distribution, or we can say, oh, let's take the most probable most probable item only. So there's different ways how you can sample from distribution, but it's the idea. So we're turning this into probability distribution over the vocabulary. Does it make sense? Okay. So each row is a distribution over the vocabulary conditioned on the previous tokens. X, so here's the indexing, which will be very nested, but this, you get a rough idea because we just discussed about this here. We are only looking into the previous context at each position. So we can generate the next word at each position. Okay, so this brings us, we kind of developed this not from scratch, but by just turning BERT into GPT, but here the GPT again, like how it really works. Like we're zooming in from the very high perspective into the very tiny perspective. So again, we have the input embeddings, which are, again, positional embeddings and token embeddings. Nothing has changed. Then there is this transformer decoder layer. Now it's not encoder, it's decoder, but eventually the only difference here is that here in this there is this mask, the mask softmax. Or the mask we're talking about, the causal mask. If we zoom in, and here this is the final layer, and this is the probability distribution. So each row corresponds to probability distribution over tokens in your vocabulary. When we zoom in into each of these transformer layers, again, so this we saw this in the last lecture on BERT. So there is layer normalization, summation, layer normalization, then. Okay, what is this? What is linear layer and then some nonlinearity and some linear layer? How do we call this? How do we call a thing where we just have a linear layer, nonlinearity, linear layer, nonlinearity, linear layer? The basic building block of deep learning. It's a feed-forward network, or another name for that, multi-layer perceptron, a concept known from 1967-ish. It wasn't that deep, but anyway, so basically linear layers with some activation in between. Here we're using the GELU, which is something like ReLU, but a little bit smoother at 0. So, and the flow is also interesting here. So, we're passing the input after layer normalization, we're passing through this masked self-attention we talk about, very much in detail, but there's other things where we just pass the input also just as it is, and then summing them up. How do we call this thing or this thing? Do you remember this? It's a special name, maybe we didn't talk about it. It's called residual connection. Residual connection. And the question is, why is it important? Why is residual connection interesting? So, why can we just, we just basically branching here and summing together. And in the branch, like one branch of this pass of the information from one layer to another is keep it, and the other is like, do some very crazy not transformation, just look at all the context, all the context tokens, make the masking and attention, and just pay attention to something and give me some value, and just all these things, like all these heads, which is very complicated. And now we're summing them up together. So, but we're still having this kind of direct pass of the information. So why this could be interesting? Why this helps? Sorry, you in the back. So you wanna pass information as it is, and maybe on the side doing some crazy things with attention, and maybe if the attention is not helpful at this moment, you wanna still keep the information flowing from the input. Because basically, if you stack this up together, so this is just one layer, but these are just one after each other. So it means there's a chance for the input embeddings to pass through the whole network to the very output through these residual connections. And from your side, it's left to right. Okay, sorry, so left to right. So they're passing from the left, and through this residual connection, there's always the information from the input embeddings to the very end. And there's the branches, self-attention, feed forward, self-attention, feed forward, self-attention, feed forward. So, and maybe, this is very important in why this fast kind of transfer of information from the input to the output could be interesting. For learning, of course, in learning, this plays a role. And the idea is that, or that's what I've heard at least. I don't have any scientific evidence for that. But what I've heard is that in the beginning of the training, you wanna these residual connections play much more important role, and after some pre-training of the network, the attention start taking over and learn something more meaningful. But I don't know exactly, so I don't recall. The point is, if you look at the sum here, this is also cool. Why? So how the gradient is propagated from the sum? So how is the local derivatives of sum? Why do we need local derivatives of sum? Because we're propagating through this convolutional graph.
One or the other. One variable is always treated as a constant and disappears in the array.
Isn't it even simpler? So let me see. We have y is a plus b. Oops, a plus b. So what is dy with respect to dA? What is dy with respect to dB? So okay, we have local derivatives here. So the derivatives from here to here will be 1, and the derivatives from here to here will be 1. So what are we doing with the derivatives in the convolutional graph? Like chain rule. What are we doing with derivatives? We have the derivative at the end of the network. Sorry, for you, at the end of the network. And we're doing backpropagation by chain of rule chain. We're multiplying these local gradients. What happens if you multiply something by 1? Exactly, that's the grade. I mean, you're basically taking the error from somewhere here. If there's an error on the output, you are propagating this back unchanged to the very input. So this is cool. There's a flow of the error through the gradient backpropagation through these things. And then you propagate them also here, and there's, you're updating the weights. So there's a chance for the error to come from the very end to the very input, and maybe changing the input embeddings as well at the beginning. So this is how you learn the input embeddings. Okay. Any questions? Okay, cool. So this is and now comes very horrible slide, sorry. But anyway, if you want to implement the thing, this is the algorithm you need. So basically, I mean, we had a similar algorithm for BERT last week, so let's do this for the transformer. But now we know everything. It's basically summarized. Basically, this is one depiction, and this is another depiction of the same thing. I like this one. I hate this one. But if you want to implement it, like some sort of, if you want to program it, maybe then it's better to see the actual algorithm. I don't think we need to go through this right now, because basically this is enough, like, to understanding the architectural things, and then we know, of course, the arrows means there's some functions going through one node, from one node to another. And there's one way how to depict it as a algorithm. But what we see here, we go through all these layers. So layer 1 until layer L. And each layer, we have this layer normalization first. Okay, so this is the first one, layer normalization. Then we have, this is the residual connection. So we're summing up the x plus the output of the multi-head self-attention mask. Okay, good. So we have a function somewhere for doing this. Then there is another layer normalization. Okay. And then there is, again, residual connection here. Oops, sorry. Residual connection here again, the sum. And here, this is the NLP or feed forward or however you want to call it. And then we do some more layer normalization at the end. And then we're projecting into the output space, which is the space of the vocabulary, and running softmax on that. Well, okay, this is it. This is GPT. No, seriously, this is GPT. Why is it so good? Well, who knows? It's been trained on many data. Yes?
Generate text, just run it over and over and always generate.
We have the generation in the next slides, so just stay tuned. So this is the forward pass of the model. There are some differences between the BERT model and the GPT. Is the ordering of the layer of normalization, so line 6 and 8. Okay, it's a tiny little detail. So in BERT, I think the normalization was after the sum, and here it's before. For empirical evidence, maybe it works better. Who knows? And what else? No final layer projection, attention with left to right. I mean, this is the most important part. So left to right attention in decoder models, because obviously you want to attend only to the past and not to the future, because you can use this then for language modeling. Training. So this looks to me like stochastic gradient descent, right? Is this stochastic gradient descent? So who thinks this is a stochastic gradient descent? Raise your hand. Who thinks it's something else? Okay, so why is it stochastic gradient descent? What are the features of stochastic gradient descent that are shown here? Okay. So we have some gradients. We have this. Okay, fair enough. We have gradients. Anything else?
We're doing like these multiple iterations of learning, like playing over and over.
We run over epochs. And we're running over training data. That's good. So we have some sequences. So these are sequences, and we're sampling from the sequences. We can take the batches. We can. I think there's no batches actually, but we can do it like the standard, mini batch. Obviously, this could be like a standard online stochastic gradient descent algorithm. So we are running over some number of epochs. How do we know? How do we know the number of epochs? What is this? What could be number of epochs?
Comparing the choose, depending on how much time you want to spend.
Our budget. This is number of epochs. So if one epoch runs for 3 days on 160,000 GPUs, you think wisely how many epochs you're going to run it. So, but of course, the more the merrier. The longer you train, the better. But you have to pay attention to other factors, roughly. Okay, number of epochs, then we're iterating through the data. Okay, so now we're taking here, so let's go. Okay, so this is something like gradient descent, absolutely, because what we are doing here is we are computing a loss, we're taking the gradient of the loss. What is a gradient? What is a gradient? Everybody knows what's a gradient. What is a gradient? Any idea? Yes. Okay, more. Okay, so try to be more concrete. Like more concrete, yes.
Vector in the steepest descent.
Almost, just by factor wrong.
Oh, essence.
Exactly. So the gradient is basically mathematically, gradient is a vector of partial derivatives of some output with respect to inputs. What are the inputs here? In the gradient, what are the things? So we have some. Okay, what is the output? So typically, it's the loss with respect to what? The parameters. We're updating the parameters. We're in the parameter space. So we need to know for each parameter of this, let's say we have the parameters, which is a vector of parameters W1, W2. You can sort it as a vector. I mean, these are matrices and the layers and things like that, but you can basically think it as a bunch of numbers. Parameters are a bunch of numbers. They can have names. So you want to know the partial derivatives with respect to all your trainable parameters. Okay, how many parameters are in GPT? Say again? Few billion. Could be like 112 million for a smaller model to a few billions, like 70 billion models, 7 billion models, 70 billion models, who knows? So you have this billion size dimensional space and you have the gradient in there. And this is gradient showing you for each input, or so for some other constants, which are now the input, what is the steepest ascent, what is the direction of the steepest ascent. So then you multiply this by learning rate and take the opposite direction. So you go down. Down in a way like to the small loss. And you update the parameters. Okay, so everybody should know what is a gradient. Like you really should know what is a gradient. Anyway, so we have the gradient here. And what is in between is that, okay, so we're running this function d-transformer over inputs and we're getting the matrix of this is the length, the number of rows is the length of the input, and the columns is the size of the vocabulary, because we're projecting into the vocabulary space for prediction. And now here we are running this very awful function which looks like, I don't know, what is it? It's negative log likelihood, which is something like cross entropy. It's the same thing. And let's have a look how to compute this. But otherwise, this is just a standard SGD. Any questions? Cool. Should speed up. Let me see. How many slides do I have? Oh, so many. No, come on. No. Okay. I thought it's going to be a short lecture, by the way. But, you never know. So the cat said, okay, so we have the input here. Okay, let's give it a shot. We have so we talked about the negative log likelihood in the last lecture of BERT, but let's do it again here for the GPT decoder. So the cat set is the input, so these are the input token IDs. Because why not? This is how we kind of design our tokenizer, and they correspond to something. After running through the GPT transformer, we have 3 rows, because why? Because 3 inputs, and this is size of the vocabulary, which is, I don't know, 50K. And these are probabilities. So again, each row is a distribution over the vocabulary. So this is the input. So we have the get set. Okay, so far so good? Good. Now, okay, so again, this is what we had from the previous slide. Now we are at position 1. So for position 1, the model should learn to predict cat, which is the next word. Right? I mean, we're predicting always the next word. So at position 1, we are at token V. The next word was cat, and we should be able to predict cat from the previous context. So the gold standard now is one-hot encoding of cat. And as we saw, the cat here, so the cat corresponds to position in vocabulary 11,987. Which means if we turn it into one-hot encoding, it's all zeros except for 1 at position 11987. One-hot encoding of token, okay? Any questions? One-hot encoding? We spend a lot of time on that. So this is the gold standard. And the prediction, of course, is the row, the first row. Now we're indexing by 1, okay? Not by 0. The first row. And this looks like exactly this. So this is exactly this row. So we have this prediction y hat, and the gold standard is y. So far, so good? Okay. How does cross-categorical a categorical cross entropy looks like is that it's summing over all categories, so over all inputs in the vectors. So we have two vectors, right? We have the predictions and we have the gold standard vector. And by definition of the cross entropy is that for each of the positions, we're taking y and we're taking the logarithm of the prediction. And we sum them up and there's a minus at the beginning. Okay, so in fact, as we see here in the gold standard, everything is 0 except for the position yk here at 1. Okay, so we can just kill the sum and this will become 1, and we just take the logarithm of position, of these two. I mean, if we align these two vectors, everything else will be 0, so we just don't care about in the sum, and we just take the probability of this, the value of the probability at the position of the gold standard. So this is how we go from this into this formula. Make sense? Okay. So what else? Which basically means like, okay, let's get rid of the 1, so it's minus logarithm. Now we're saying, okay, we're slicing, so the y hat is actually a slice from the P matrix on the first row. Okay, yeah, right, I mean, this is the vector. So we're saying, okay, let's slice this first vector and minus logarithm of this vector. And, okay, which means this is as well slicing the first row and taking, what is xn 1 plus 1? It's 2. Yeah, exactly. So it's the second output, which means, so there was a bar which is a probability distribution of the first token. Sorry, this is, what is this? Okay. Oh yeah, no, come on. This is so 11987 is the next token ID, which is xn, right? Xn at position 1 plus 1 at position 2. Oh, right, okay, so I'm predicting this thing. Oh yeah, okay, this is how I get this number. So this is basically xn at position plus 1. And if we are at position t, this will be always the next token ID. So this is how we got like backwards from categorical cross entropy, which we know it's just how you compare two softmax distributions. How did we get this very awful lock here? Okay, so this now we understand. It's basically cross entropy for the next token. And we do it for, here's some crazy things in between. We're doing for what? For all the previous tokens. So we compute a loss for this position, from the first token until the previous token, because we're iterating over, so we compute this basically for each of the inputs. So for each token, we compute a loss at this input, and the next token we compute a loss, and the next we compute a loss, and the next we compute a loss, and we just, sum them up. Do we? I guess so. Yeah, why not? Or do the backprop. This is interesting. So we spent some time like dissecting basically GPT, so we'll look into the implementation because you can do it in many different ways. But the idea is that you compute a categorical cross entropy. And then if you do it for position 2, the same things will happen. So any questions about the loss? It's basically a cross entropy loss as we saw it in every other machine learning. Okay, prompting. You know what? Let's keep it for next week because I don't want to. Oh no. We'll finish. We'll still have like 15 minutes, right? Good. Let's finish. Prompting. Okay. So prompting is basically you have the model, you put input in the model, and start generating the tokens afterwards. This is it. This is prompting. Like everybody's doing that. Like, you type something in ChatGPT, and ChatGPT will tokenize the thing, and then take all these inputs, run the model, and do the prediction for the next token, and then take the whole thing again, run the next prediction, and stuff like that. So this is basically the algorithm. So it's called inference mode, like decoder inference. And for the length, so for all of the tokens, we basically run it through the transformer, transformer model, transformer thing, to get this matrix of for each token probability distribution over, for each input token probability distribution over vocabulary. And then this will help us for the last token to get the probability distribution for the next token. So the P will be probability distribution of what's coming after this token. You know, it's like in the standard language modeling. Like, what is the probability distribution of the next token? So if you have probability distribution over vocabulary, you can do, as we said, like, you know, how you get the next token, how you want to basically, what do you want to deal with that? How do you want to deal with it? So we say, okay, you have a probability distribution, let's just do a random sample. So you have some random seed, and you have this discrete distribution. It's like a sample from the distributions, which means very likely you get tokens which have high probability. Unlikely you get something which is low probability. Okay, fair enough. You can do this. You can take the maximum probability token, so always, you know, the one which is like the most likely, or you can do something in between, or you can kind of steer the sampling by this tau. What this tau could be? It sounds like physics, right? Tau sounds like physics. It's the temperature. No, it's exactly the temperature. Temperature. So, and we, as far as I remember, lecture 2 or 3, we have the temperature in the softmax. So if you go back to the slides, we have like a couple of examples. In the softmax, basically, if you have a low temperature, you have much more, how was that? Now I mixed up. Like with low temperature, you have much more uniform distribution, and if you have high temperature, you get basically all the spikes. So everything will be on, you know, everything will be basically zeros and ones. So you can, with temperature, you can control the randomness in the sampling in a way. And basically, you know, I don't know if you can set up temperature in GPT. Can you set up temperature in like ChatGPT? Is there a parameter for that, like temperature? Maybe not. So maybe not on like the user interface, but most of the models which are running, for example, at Hugging Face, and you can test like there's parameters, and temperature is one of them. And you know, if you have different temperature and different random seed, the thing is, the sampling is random. This is interesting. So if you randomly sample from distribution, every time you repeat a thing, and if you add another random seed, you will end up with different sequence. That's why if you ask ChatGPT about things, you get this not always the same thing for the same input, because there's randomness. Whereas the randomness, exactly, it's in the sampling here. How do you make sample reproducible? You put a random seed the same. So there's a random how's it called? RNG, random number generator somewhere, and it could be seeded. If you seed it with the very same seed, and you have the same architecture and all the nitty-gritty details about, you know, torch randomness and GPU randomness and all these things, if you set it properly, you should get the same output for the same input. Typically, it's a little bit hard to get the same thing. Like reproducing the exactly same output is kind of tricky, you know, because the randomness is kind of, I don't know, looks hard. I don't know why. You have just GPU, CPU, and random seeds and a couple of frameworks, but it looks tricky somehow. And then you add this sample token Y into your list of the tokens and go next until you run out of ideas, or end of sequence token could be like the EOB, like EOB, EOS, end of sequence token. So once you generate end of sequence token, you finish generating, and then whatever. Okay? Any questions? Sampling? I think we try. We should try. Okay, so let's finish with. No, let's keep it for next time, because I will be talking more about GPT-3 models, but today we talk about the architecture. So summary, do we have summary for today? Well, the main take-home message is like self-attention is powerful, and if you wanna do this for language modeling, where you attend to previous tokens, you just use the mask. How to use the mask is this very kind of neat trick of masking these minus infinities, and the rest will stay the same as in the BERT model. So I guess this is it. Any questions? Okay, let me just stop recording, and then we talk about the exercise.